Hello everyone, so I am doing another video tutorial on the t-table, but this time I will be focusing on how to find the relevant area. So last video tutorial focused on how you would find the t-score, and that is t sub alpha over 2 for a confidence interval formula. But now I'll be focusing on area information because area is really what we care about when it comes to the rejection region method of hypothesis testing. In particular, there are two areas that we are interested in. The first one is alpha, the maximum probability of committing a type 1 error, and the p-value, which is the actual probability of committing a type 1 error. Okay, so I'm going to start with alpha. So suppose that you are doing a 90% significance test. And you want to find the boundaries of the rejection region. So let me go to my sampling distribution. So if you're doing a 90% significance test, that means the middle area is 90% of the curve in terms of proportion, that is 0.9. And in order to get the boundaries of the confidence interval, we already did that last time, but remember that these boundaries here, the boundaries of your confidence interval, are also the boundaries of your rejection regions. So t sub alpha over 2 is exactly the same thing as a t star, or also known as critical t. So if I were doing a 90% significance test with a hypothesis test, the middle area equals 0.9, and my rejection regions are these red areas. They add up, both of them add up to 1 minus 0.9, and that's alpha. So in a 90% significance test, alpha is 1 minus 0.9, or 0.1. But each of these red tails are identical to each other, right? They are exactly the same size. The area of each of these tails is simply alpha divided by 2. So given that our alpha value was 0.1, if we divide that by 2, we find that alpha over 2 equals 0.05. So the size of this red area is 0.05, and the size of this red area is 0.05. Together, 0.1, and then the rest of the sampling distribution has an area that's equal to 0.9, all adding up to 1 or 100%. Okay, so we already know that this is the different t-scores I get for that boundary depending on my sample size. But today I'm going to focus only on these first 3 rows that give me area information. So third row says 2 tails. So that's alpha. That gives you the area of both of your tails, both of these red areas. So that's alpha. So that is equal to 0.1 in our example, right? So 90%. Take it up to the third row, you get that 2 tails is equal to 0.1, the area of both of your rejection regions, both of your tails. So this is the same thing as alpha. And then right above that, you have 1 tail. So that is simply the area of only one of these tails, one of your rejection regions. So that's alpha over 2. And you'll notice that alpha, divide that by 2, alpha over 2 gives you 0.05, alpha over 2. And then the subscript in the first row is cumulative probability. That simply means the area to the left of your boundary. So for a 90% significance level, the boundary of your right rejection region is right here. Cumulative probability is this entire area to the left, including this red tail. So the entire area to the left is 0.9 plus 0.05. So that is this subscript right here, the area to the left of your boundary of your confidence interval, which is also the boundary of your rejection region. So this is the area information that I would get if I were looking up T sub alpha over 2 or T star. But if I look up my sample t-score, then I'm going to get p-value information. All right, so in our example, first hypothesis testing example that we did, we found that our sample t-score is equal to positive 1.78. So if you have support for the second substatement of your alternative hypothesis, you will get I forgot what I started the sentence with. If you have support for the first substatement of your null hypothesis, then your sample t-score will be negative. And if you have support for the second substatement of the alternative hypothesis, then your sample t-score will be a positive one. So now our sample supports the second substatement. So that's why we have a positive sample t-score, because our sample value was 52.8, which is greater than 52. All right, so that's why we have a positive sample t-score of 1.78. So now we have the boundaries, and then we have our sample t-score. So comparison of the boundary and the sample t-score tells us whether our sample is in the rejection region or not. And our conclusion is that for 90%, it is in the rejection region. But for any higher significance levels, our sample is outside the rejection region. So now in step 5, we actually look up this sample t-score to give us the p-value. So I'm going to go back to my t-table, and our sample size in this example is 100. So that's N, not DF. DF is N minus 1, 99. So in this case, we don't see 99. We have an 80 and a 100. We are rounding down to the next lowest degrees of freedom on that table. So this is the relevant row to us. So in order to get the p-values, if I were to look up the critical t-score, t-star, then it's 1.664. That would give me the alpha information that I talked about in the beginning of this video tutorial. But if I look up my sample t-score, that is going to give me my p-value. So T-star, if you look it up on this table, gives you alpha information, but sample t-score gives you p-value information. So I'm going to look up 1.78 on this row, and you'll notice that t-scores are getting larger as you go from left to right. And my sample t-score is in between these two columns. 1.78 would be right here. So I'm in between these two columns, and I'm going to take this up to the top of the t-table. So again, my sample is in between these two columns. And just like with critical T, T star, and alpha, these three rows give me the same information. So my sample is right here. The subscript gives me the area to the left of my positive sample t-score. So my sample is right here. So the area to the left of my sample, where the t-score is 1.78, is between 0.95 and 0.975. And then if I go to the second row, that's going to give me P over 2. So P over 2 is the area to the right of my sample with a positive t-score. So the area to the right of 1.78 is between 0.05 and 0.025. So let me go back to this sampling distribution. So this is the boundary of the rejection region for 90%. That is equal to 1.664. And my sample is larger. So my sample is somewhere here. It is to the right of that boundary. So this is my sample. T is equal to 1.78. And if my sample is here, the area to the right of it is P over 2. So the area to the right of the boundary gives me alpha over 2. The area to the right of my sample gives me P over 2. So this is what this row gives me. The area to the right of my sample is between 0.05 and 0.025. So you would think that, okay, this is my one sample t-score. I had one sample which had a t-score of positive 1.78. So the area beyond it is this area. So that should be it. But no, you have to actually multiply this area, P over 2, by 2 to give you the actual p-value. And the reason is the following. So remember that, yes, we only have one sample, which gave us a positive t-score. We don't have two samples. But remember that our alternative hypothesis has two substatements. When I say mu is not equal to 52, one possibility is that mu is less than 52, and the other possibility is that mu is greater than 52. So we know that only one of these substatements is relevant to our sample, because in our sample, we observe that x bar is 52.8. X bar is greater than 52. So this is the only relevant substatement to us. However, the entire hypothesis test includes the first substatement as well. So it may not be relevant to our sample, but when we write our alternative hypothesis in this way, we say mu does not equal to 52. This is still one of the possible substatements. So our alternative hypothesis has two substatements, even though only one of them is the relevant one. And in order to do a complete hypothesis test, we need to consider both of these substatements. So even though our sample is only in the right rejection region because our sample t-score was positive 1.78, we also have to not ignore the first substatement. So in order to not ignore the first substatement, I'm going to take the negative version of my sample t-score, So my sample t-score was positive 1.78. I'm going to take the negative version of that, negative 1.78. So it's going to be somewhere here. And I'm going to also look up the area beyond the negative version. So positive 1.78, the area beyond it gives me P over 2. Take the negative version of it, negative 1.78, look up the area beyond it. That gives me another P over 2. So what I'm doing is taking the P over 2 value I get from the second row, and that was between 0.05 and 0.025, doubling it, meaning I am accounting for both of the substatements in my alternative hypothesis. And this is what gives me my p-value. So this is the complete hypothesis test. Right? So again, I am looking up my sample t-score, which is between these two columns, 1.78. So my sample is in between these two columns. And then it is the third row that gives me the p-value. So my sample is here. So my p-value is in between these two columns. So my p-value is between 0.05 and 0.1. So again, this t-table is meant to fit into a nice single page, so we don't have every single area information. So again, unlike our z-table, which is very, very detailed when it comes to area information, the t-table doesn't provide that much detail for area. But again, you can go ahead and use a p-value calculator. There are a whole bunch of them on the internet. This is the one I like to use, the p-value calculator. So in this case, it's a t-distribution you have. You can also look it up from a z-score. So this is from a t-distribution. I'm going to look, it's 1.78 is my t-score. My degrees of freedom, remember, I had 100 observations. So my DF is a 99. So when I put in this information and click on compute P, it gives me a very precise p-value. So whereas here you're saying that my p-value is between 0.05 and 0.1, here you'll see that it is actually 0.0781. So in order to figure out our significance level, we will compare this to various alpha values. So this is step 5. Based on my p-value, this 0.0781, or even if you use a t-table, it's between 0.1 and 0.05. It's neither one of these actual numbers. It's some value less than 0.1 and some value greater than 0.05. Even if you use the t-table, which is not super precise, you'll get to the same conclusion, right? So this t-table is designed to be detailed enough to give you conclusions when it comes to the classic significance levels, 90%, 95%, and 99%, and 99.9%. So if I were to compare my p-value to an alpha of 0.1, so that's the alpha for 90%, that p-value is less, meaning I can reject the null hypothesis at the 90% level. But that p-value of 0.0781, that is less than all remaining alphas of 0.05 for 95%, 0.01 for 99%, and 0.001 for 99.9%. So based on this p versus alpha comparison, my significance is 90%. So when it comes to finding the p-value, you can Either use a t-table, focus only on your relevant DF. Again, you would be rounding down to 80. Locate your sample t-score and take it up to the third row. That gives you your p-value. And again, if you were looking up critical t-score and take it up to the third row, that would give you alpha information. So when you look up critical T-star values, that gives you alpha in the third row. And when you look up your sample T-score, it gives you p-value information in the third row. And of course, the p-value calculator is another option available to you to give you p-value.